Good evening, everybody. Welcome to SLU. If you're listening, you're tuning into my Intro to Astro crash course given Wednesday nights at this time every week. If you're joining me tonight and also joined me this morning for our super blue blood wolf moon lunar eclipse, then thanks for hanging in there. It's been a long day, but there was a nice stretch in between, so maybe you took a nap. I did not, but I wish I did. But tonight, actually, we are going to venture away from the moon. So unfortunately, I already did a moon course, and so I don't have another one for you tonight. I hope you got your moon fix this morning, but we're going to venture further out into the universe, and we're going to talk about galaxies tonight. Last week, we talked all about the Milky Way and a little bit about Andromeda, and this week is a promised course on galaxy classification. So I am going to share my screen with you. So if you are listening at slu.com, you're going to want to pop over into the space situation room where you can see my screen, because I'm going to be sharing some images with you tonight from my SLU picture file, and also some special diagrams to help show what we're going over. So galaxy classification, I think the first place to start is in the title. And the fact that we are able to classify these means that there must be enough of them that classification is important, and also that classification is doable. If you only have 2 apples, how can you classify them if they're both red? If you have one green and one red, then you're lucky. But if they're both red, you don't know if they're the same apple or if they're 2 different kinds of red apples. If you have 10 red apples, you might be able to make some different categories based on their shading and their size. So this is kind of what we're talking about when we talk about galaxy classification. Back before the 1920s, it was thought that all of the white dots in our night sky, everything that you could see with the naked eye, was within our own galaxy, was within the Milky Way. They did not know that there was anything outside of the Milky Way. They thought the entire universe was contained within it. 18th century philosopher Immanuel Kant was one of the first people to theorize that the Milky Way was maybe not the only galaxy, that maybe there were more. And he coined the term island universe to describe a galaxy, thinking that the Milky Way was its own universe, and maybe there's others out there that are other mini universes. In the 1920s, Edwin Hubble was the first to confirm that the Milky Way was actually one of many, many galaxies. He did this by studying a variable star called a Cepheid variable. And a variable star just means that the light from the star is not steady, it varies. So it can vary over very different time scales, but being able to measure the varying brightness of the star, essentially it pulses. And being able to measure that allowed him to measure the distance to the star. And this variable star was contained within a nebula. So a nebula is a cloud of gas and dust in the universe. It's like a fuzzy dot looking thing, as opposed to a sharp white dot that is a star. So these fuzzy nebulae, they thought were all contained within our Milky Way, as everything else they thought was. When Edwin Hubble measured that this variable star in this nebula was actually further away, really, really far away, further than the edges of our galaxy, he discovered that there must be other galaxies out there, because this nebula was not contained within our galaxy. And actually, not all of the nebulae that we have are in our galaxy, and we're going to talk about that next week. But since then, there have been theorized that estimated that there's over 100 billion galaxies in the entire observable universe. And they range from dwarf galaxies to giant galaxies, where dwarf galaxies have as few as a couple million stars, and giant galaxies have over 100 trillion stars. Edwin Hubble made what we call the Hubble tuning fork. It is a way to classify galaxies, and it describes all the different types that there are, and we're going to take a really in-depth look at that tonight. When you see a dwarf galaxy, you'll often find it clustered around larger galaxies, kind of how near the Milky Way we have the small and large Magellanic Clouds. And so frequently these galaxies lose their stars to their larger galaxy near them via gravity. They pull the stars in through like a stream, and we can see our own galaxy doing this, and we know that our galaxy has cannibalized other dwarf galaxies in the past. The stars stream across the sky as the dwarf galaxies are being basically torn apart. We see this happening with the Large and Small Magellanic Clouds. Galaxies themselves are mostly empty space, actually. So when we look at an image of the Milky Way or another galaxy, or even another galaxy, sometimes it's very hard to make out the individual stars. And you might think, well, they're just so densely packed. But in fact, if you shrunk all of the stars within galaxies to the size of oranges, this was my favorite analogy that I found online today, to the size of oranges, they would be separated by 3,000 miles. So hold an orange in your hand, and then the next orange would be 3,000 miles away. That's how far in relation the stars are apart based on their size. More, not 3,000 miles, it's a ratio. So if the star was as small as an orange, it would only be 3,000 miles from the next star. But in fact, they're much, much larger and so much, much more distant away. So galaxies are actually mostly empty space, which is why I mentioned last week that when Andromeda collides with the Milky Way in 4 billion years, our solar system, if it would still be here, if the sun wouldn't have engulfed the entire thing by then, probably would be unaffected, because stars are so far apart in galaxies that we would probably get through unscathed without anything actually bumping into us or affecting our gravitational pull from the sun. So let's take a look at the Hubble tuning fork, which I mentioned was Edwin Hubble's classification scheme of galaxies. So it really is a tuning fork shape. Again, this is where you're going to want to follow along with me in the space situation room if possible. And so there's 3 major types of galaxies: ellipticals, spirals, and irregulars. You'll notice on this tuning fork that there's only ellipticals and spirals. And that is because irregulars, as they sound, are irregular, and they have no regular structure, no symmetrical structure, not a structure that can be classified. They're divided into 2 groups called irregular 1 and irregular 2. And irregular 1 galaxies are regions that have elemental hydrogen gas and a lot of young hot stars in them, whereas irregular 2 galaxies have a lot of dust that block most of the light from the stars, which makes it impossible to see the individual stars in the galaxy. Irregular galaxies are usually the result of a collision between galaxies or gravitational interactions, such as cannibalism between galaxies. We don't really suspect that they would have formed on their own in that weird irregular shape. But so if 2 galaxies merged, when Andromeda and the Milky Way merge together, they're both spiral galaxies, and they will probably form an elliptical. But depending on how the merge goes, depending on the size of the 2 galaxies involved, it could form an irregular galaxy. So then we're left with ellipticals and spirals. And if you look at this tuning fork, the ellipticals are the handle, and the spirals make up the fork arms. So this is because there is one branch of elliptical galaxies, and within it we categorize based on the shape of the elliptical. But spirals, there's 2 different kinds of spiral galaxies. There's the regular spirals, and then there's the barred spirals, which are also broken down into the way that their structure looks. So we'll talk about ellipticals first. Ellipticals have very little gas and dust because the gas and dust are found in the clouds, and they're the birthplaces of stars. So we expect that there should be very few young stars in elliptical galaxies because they don't have much gas and dust. So elliptical galaxies pretty much have the oldest, reddest stars in the universe, and they're known as population 2 stars. Population 1 stars or young stars. Elliptical galaxies vary widely in size. The largest and smallest known galaxies are both elliptical. Very large elliptical galaxies can reach over 300 million light years in diameter. For reference, our Milky Way is 100,000 light years in diameter. A dwarf elliptical, which is a very common form of elliptical galaxy, may only contain 1/100,000th as many stars as the Milky Way. Super, super small. And the Milky Way has some 200 billion stars in it. So the ellipticals are broken down, you can see here by number, E0, E3, E5, and E7, and this is based on their shape. So an E0 is a circular galaxy, actually spherical because they are, of course, in 3 dimensions, but when we look at them, we only see 2 dimension, so circular is appropriate here. And then the greater the ellipticity, the greater the elliptical or oval shape of the galaxy, the higher the number. So an E0 is a basically circular spherical galaxy, whereas an E7 is much more elongated. And you can see underneath the cartoon part that there's actual examples here of the galaxies. And what you're seeing is this big halo around the denser region of the elliptical. Then we break into our spiral galaxies. So right before we break into the actual spiral shape, we have what we call an S0 galaxy. This is kind of an intermediate type between an E7, a really elongated elliptical, and an actual spiral galaxy. They're not ellipticals because they do have what we call a bulge and a disk, which is the definition of a spiral galaxy. It has to have a bulge and a disk. The bulge is around the center. It's kind of like, picture a Frisbee, and then if you had cut out a hole in the middle and shoved a tennis ball in there. The Frisbee would be your disc, and the tennis ball would be your bulge. And then all around the entire thing, we have what we call a halo of stars. But the bulge and the disk are what form, the disk is where the spiral arms are. And so an S0 galaxy does have a bulge and a really thin disk, but they don't have any spiral structure. There's actually no spiral arms to them. So we call these lenticular galaxies. If the disk is really faint in a lenticular galaxy, it's easy to mistake it for an elliptical, because if you're looking even just here at this tuning fork, you can see in the cartoon at least that it doesn't really look that different from an E0. When we look at the actual galaxy itself, we can see the bulge versus the disk, but if the disk was really faint, you would just see this bulge area and you might think that it's an elliptical galaxy. So spirals, the first branch, which is a regular spiral galaxy, it has a bulge, it has a disk, it has a halo, and in the disk are spiral arms. And so depending on how many spiral arms and their tightness, we assign 3 different letters, A, B, or C. So you can see the cartoon example here and then real examples above it. So an SA galaxy would have probably just 2 major spiral arms, but they're a little bit thicker and harder to make out. An SB galaxy, you really start to see more of a spiral structure with some thinner but more quantity of spiral arms. And then an SC galaxy, you see very thin spiral arms, a lot of them, and they really start to branch out away from the bulge. The second type of spiral galaxy is a barred spiral. So we also break this down into A, B, and C. We have, what this means is that through the bulge, in a regular spiral galaxy, the spiral arms come directly from the bulge. In a barred spiral galaxy, through the bulge is a bar of stars, and then off of the bar is where the arms come from. And so actually our Milky Way is a barred spiral galaxy. We do have a bar running through the center. So we call these SB galaxies. And so an SBA galaxy has 2 tightly wound arms coming off of the bar, whereas an SBB galaxy, the arms start to spread out a little bit more and they're a little bit thinner. And then an SBC, they really are widened here. You can see we're almost even losing the spiral shape maybe a little bit because the arms get so wide. So we have E galaxies, we have S galaxies, and then we have SB galaxies. And if you're curious, irregular galaxies are abbreviated as IRR. I guess. In the spirals, so elliptical galaxies I mentioned are mostly made up of older, redder stars, just the entire thing. They don't have a lot of gas and dust are what make stars. So clouds of gas and dust are what form stars. And so if we don't have gas and dust, then we aren't forming new stars. And if we're not forming new stars, then we must be full of old stars. Spiral galaxies are different. The bulge mostly contains older stars in the center, but then the disk is made up of dust and gas, and so they're star-forming regions, and they have much younger, bluer stars. And this red and blue is referring to cool and hot. And so don't think your kitchen sink where red is hot and blue is cold. It's actually the opposite. So redder stars are cooler, and bluer stars are hotter. They burn much hotter, and they're younger. Then the halo, which is the big, really, really big spherical shape of stars distributed around the entire galaxy, contains old clusters of stars known as globular clusters. And these globular clusters are thought to be some of the oldest stars in the galaxy. They formed in the early universe and never made it into galaxies themselves. They never grew to be their own galaxy, and so they just kind of got gobbled up by other clusters that did form into galaxies. But they were strong enough to stay in the halo on their own instead of getting sucked in. And so we can find a lot of information about the early universe in those globular clusters because they're so old. So let's look at another example of this Hubble tuning fork. You'll find many examples of this on the internet. This is not the only one. This is just one of my favorites because it really illustrates the different classifications so well, and it also shows real examples of the kind of galaxies we're talking about. Here's another example of a Hubble tuning fork, and this is showing real examples. So we have ellipticals, barred, and spirals, and if we look, we can really see the difference here. So this elliptical E0 is incredibly spherical, whereas the E5 is starting to be much more elliptical. When we look at our lenticular galaxy, we do see a nice disk here. We don't see any spiral arm structure, which is why it's an S0 or lenticular, but it might be an SO. I keep saying S0. My apologies. But if we couldn't see the disk, then again, this is why it looks somewhat elliptical. And actually, sometimes you can't even make out the bulge instead. So you might see the disk and not really be able to make out much of the bulge, and so it might look super elliptical. We have our normal spiral galaxies, where we have thicker spiral arms, and then we spread out into thinner, wider spiral arms through ABC classifications. And then our barred spiral galaxies, where we have a bar structure running through the center that the spiral arms come off of. So this is just another example of the different types of galaxies that you might see. So I'm going to hop over to our website, and I'm going to show you some of the images. Unfortunately, the Canary Islands, our telescopes are offline tonight because there's still some ice and snow up there on the mountains, and so we won't be able to look at live galaxy pictures tonight through there. Chile is coming online tonight. It's clear, so it should be on at 8, but my show is over by then. So I'm going to be showing you some galaxies images that I already have in my photo roll. So if you were following along, you go to telescopes, you go to my pictures, and then you can either sort by missions or photo roll, depending on, if you click on a mission, you might have, well, that only has one because that was let me go back. I go through my images and kind of clear them out a little bit sometimes. But anyway, here you go. Here's an example of a mission you might have multiple images within. Otherwise, you go to your photo roll and it breaks apart all of the missions into their individual images. And also, if you took any images, like I took one of the SLU Solar Telescope, it was a live feed and I just clicked take image. So that would be in my photo roll. So I'm going to filter by galaxies, because I have a lot of pictures and I want to just show you the galaxies. So this is my collection of galaxies that I've taken with our SLU telescopes. This is one of my favorites. This is Andromeda. How beautiful is this? I'm going to zoom in just because how can you not? Look how gorgeous that is. You can see here's the bulge, and here is a nice spiral arm, and here is another one. But I didn't just come here to show you Andromeda. I did come here to show you all of my galaxies. So let's go back to the photo roll. Sorry, my computer is pretty slow. Bear with me. Running my video stream doesn't help. So here's another one, a very great image of a spiral galaxy. This is the Silver Coin Galaxy. You can see the two spiral arms coming right off of the galaxy here. Beautiful, and a super thin disk again. We can look at, this is called Robert's Quartet. I might have to zoom in on this one for you. And so this is a really great example of actually how we see galaxies before we know to look at them. So if you look up at the sky, and this is a good example actually too of what the early astronomers and philosophers thought they were looking at when they just called everything that wasn't a pinpoint of light a nebula. So you're looking at this image here and you can see the stars, star, star, star. These sharp pinpoints of white light are stars. But then you have these fuzzy looking things. And so this is the kinds of things that they all called nebulae, because they didn't know what they were, and they thought that they were all contained within our galaxy. So why would they think that they were other galaxies? And of course, it turned out that they were. But so if you look really closely, this is called Robert's Quartet. So there's 4 galaxies here. You can make them out because they're the fuzzy patches. And yes, sometimes fuzzy patches are nebulae and not galaxies, but in this case, I know that they are. And you can actually, if you look really, really close, you can see that this one is a spiral galaxy. You can see the bulge versus the disk. So that's kind of a fun thing to look at. I have a couple of those here as well. This is the NGC 6769 trio. The color wasn't so great, the focus in this image, but you can still very clearly make out what the galaxies are versus what the stars are. They're pretty easy to decipher once you know what you're looking for. Here in the Triangulum Galaxy, it's this one and this one. This is the black and white image. This is the color image. You can also see the central bulge and the spiral arms coming off of the bulge. You can see 2 distinct spiral arms if you look. Let's go to my next page. I have a couple in here where the focus wasn't super good, but here's an example. Oh, okay. I have about 4 more I'm going to go through. Here's the Pinwheel Galaxy M101. So this is the designation. So if anybody's curious, if you're listening and you don't understand why sometimes things have 2 or more different names, I won't lie. There are many, because my research is in brown dwarfs, and there are many brown dwarfs that get like 6 different designations based on which telescope took the spectrum of it. Things have sometimes fun names like the Pinwheel Galaxy, but then M101 is the Messier catalog, and so this is the catalog that it got its designation in. So this galaxy has beautiful spiral structure. I'm going to zoom in on it. You can see very clearly in the center, here is the bulge, and then we have one spiral arm here, another one here, and they really just look at that galactic structure. This is really beautiful. And actually, this is kind of a good example of a top-down view of what our Milky Way would look like if we were outside of it. And if you joined me last week, you'll know that any images that you see of the full Milky Way spiral structure. Now, I'm not talking about the bar. Of course, we can look up at the night sky in really, really dark places and see the Milky Way in front of us. And that's you looking towards the center of our galaxy. So the solar system is actually on the outskirts of the galaxy, located in one of the spiral arms. When you're looking towards the center, you can see this beautiful Milky Way, like the river of stars. And you're looking towards the center of the galaxy, so you're actually looking towards the bar. But the top-down view, if you see any images of that, they're artist renditions because we have never left our galaxy. So we could not possibly have an actual real image of it from the outside. It's like trying to take a selfie when your arm doesn't reach far enough to get your body in it. So this Pinwheel Galaxy is a pretty good example. But actually, I did mention that our galaxy is a barred galaxy, barred spiral. And so here's an example of I was going to say a great example, but it's called the Great Barred Spiral Galaxy. So that did it for me. Here you can beautifully see the spiral structure. So here's the bulge in the center, this white not pinpoint of light, but this white kind of big circular light. And you can see two little teeny spiral arms trying to come off of it, but then right through the center is this big, big bar. And then we have two huge spiral arms coming off of it. And so what's fun to do is to look at something like this and then pop back over to your tuning fork and try to decide what it is. So look at SBA, SBB, and SBC, and then go back to your galaxy and try to determine. So those arms look pretty thick to me. It kind of looks like an SBA, but they're also pretty wide, which kind of reminds me of an SBC. So that's interesting. And sometimes, I'm not pretending to classify this galaxy. It probably has a defined classification already, but sometimes galaxies cannot be classified as one or the other, and they'll have two different letters or numbers next to their name. So, for example, it could be an SBAB, where it looks like both an SBA and an SBB. So, just for example. Go back to page number 2. Here is the butterfly galaxies. So this is two galaxies next to each other. You can see their spiral structure as well. And they're nearly touching in this, like in our point of view. And so they look like a little butterfly. I just thought that was adorable. That wasn't the next one I was going to show you, though. I got distracted. But here is the last one that I'm going to show you tonight. Actually, sorry. I just love all of my images so much. I could do this all day. Here's an elliptical galaxy. This is a very circular elliptical galaxy, so we would call this an E0. Over here, we have what appears to be a bulge and then a disk around it, but I don't see any spiral structure. So this could be a lenticular galaxy. Now, my image is very, very fuzzy, and so I wouldn't look at this image and determine that it doesn't have any spiral structure. I would determine that my viewing wasn't good enough to say, but if I had to go from this image, I would say it might be a lenticular galaxy. Again, not the one I was trying to show you. So let's get back to the one I wanted to show you. Edge-on spiral galaxy. This is one of my favorite examples, and this is the one that I always got my students with in my Intro to Astro course that I taught. When you look at a spiral galaxy from above or below, you see the central bulge, and then you see the beautiful spiral arms around it. What if you look at a spiral galaxy from the side, or what we call edge-on? You wouldn't see the spiral arms because, remember, the spiral arms are a disk. So pretend you're holding a CD, and if you hold the CD up so that you see like the label of the CD, you know what the CD is. Now turn the CD on its side so that actually like the plane of the CD is parallel with the plane of your floor. Now you're looking at it edge on. You see the really thin disc of the CD. And now can you tell me what the CD is? Can you read the label? No, of course not, because you're not viewing it from the top. You're viewing it from the edge. This is what happens. We only get one vantage point in this universe. We can't change it. And so sometimes we look out and we get the opportunity to see spiral galaxies from the top or from the bottom, or even from an angle where we can kind of make out the spirals. But other times, our vantage point has us at the side of the galaxy and we just see it edge on, which means we just see the thin side of the disk. So here's an example of an edge-on spiral galaxy. Now, here's the issue with that. So in this image, it is very crisp and clear. You can very clearly see the bulge, you can see the thin disk, and you can actually see the disk running through the central bulge. It is very clear that this is an edge-on spiral galaxy. However, if my image was much fuzzier, or if it wasn't this clear of a galaxy in our view. You could imagine, maybe even if you squint your eyes a little bit, get your eyelashes in the way, you could imagine that looking at this could be confusing into an elongated elliptical galaxy. If the disk appeared a little bit thicker or a little bit fuzzier, if you couldn't clearly see the central bulge with the disk running through it, you might think you're looking at an E7, a very elongated elliptical. And this view of the edge-on spiral galaxy does not tell you whether you're looking at a regular spiral or at a barred spiral. So galaxy classification itself sounds like, oh, okay, I'm going to put them all into my different categories, my 10 red apples. But have you ever gone to the grocery store and wanted to buy red Gala apples, but the labels weren't there, and then the red apples next to these red apples, you didn't know the difference? I mean, that's what we're talking about here. So just because there are 3 different, very specific types of galaxies, it's not quantized just into 3 categories. It's a spectrum of shapes. And so it really is it's an art almost to be able to deduce what these are. There's many astronomers that work on it, and there's actually many citizen science projects that work on this too, like Zooniverse, where you can classify galaxies yourself. And so one of the challenges I would like to put out to you all listening is to create your own Hubble tuning fork using SLU's telescopes to image your galaxies. So I want you to create this tuning fork here with images of real galaxies using the SLU telescopes. So you're going to go to our telescopes, you're going to reserve missions to see all the different types of galaxies, and then put your own Hubble tuning fork together. I'll give you over a week to do this because it is winter in the Canary Islands, and so the telescopes are offline, fairly frequently due to weather, but like right tonight because of the snow. So you might need more than a week to do this, but definitely don't forget to use the Chile telescope, and maybe we'll say it's the end of January, so maybe by the end of February. So I'll put it on my calendar for the last show in February. If you create a Hubble tuning fork using SLU images, please send it to me and I'll share it out with everyone on my show. I'm really excited to see what y'all come up with, and I will try to do it along with you. So if you see me reserving a galaxy mission, then you could piggyback onto it and get your images that way as well. So just to show you how to do this real quick, you'll go to our website, go to telescopes. Chile's online. It's probably not a galaxy, but we'll just, yeah. Anyway, schedule telescopes. You can either do it by telescope, or you can use the SLU 500, click on Galaxies. It'll calculate the best time in telescope for the objects in our SLU 500 catalog. Again, it's taking a little while because my computer's RAM is all taken up with streaming this video. It's broken down into spirals and ellipticals for you. So you might have to either do a little bit of research to see which type of spiral galaxy is what you need to create your tuning fork, and what type of elliptical. Some of them, they all have descriptions. Some of the descriptions might help you, might not. So you might need to do some research, or you might just need to take a bunch of images and see what you can put together. But then if you want to schedule it, you click on what you want to schedule. I'm going to schedule the topsy-turvy galaxy because that sounds interesting. I hit schedule, and our system already picked the best time and telescope for me. So I hit absolutely, got it, thanks, scheduled. So that's how you're going to do it. And then you can just, download all of our images. If you're curious how to do this, I'll also show you that real quick because I know there's been some questions about that. So go to your image, you're going to click on download, then right click on your computer, save image as. And so then download them all. You can make your Hubble tuning fork however you want, PDF, whatever, and share it with me. I would love to see it. Absolutely love it. And so I'll have it on my calendar the last show in February. I will actually, let me pull up my calendar so I can give you a date. It is Wednesday, January 31st. So Wednesday, February 28th, I will show the Hubble tuning forks that were created. Okay, next week, same time, same place, and we are going to review the different types of nebulae. So in the same way that we classify galaxies, we have nebulae, where a nebulae just is a fuzzy object in the sky that's a cloud of gas and dust, but the clouds of gas and dust have different properties based on what they're made up of and their location in the sky. So we'll go through the different types of nebulae. In the meantime, you can check out Paul Cox's Practical Astronomy on Sunday at 6:30 p.m. Eastern Time, followed by Helen Avery's Constellation Stories at 9. And if you have any questions from the lunar eclipse this morning, we are monitoring Twitter, and feel free, our discussion boards as well. Ask any questions you've got, and I will see you next week. Clear skies, everybody. Discovered that there must be other galaxies out there because this nebula was not contained within our galaxy. And actually, not all of the nebulae that we have are in our galaxy, and we're going to talk about that next week. But since then, there have been theorized that estimated that there's over 100 billion galaxies in the entire observable universe. And they range from dwarf galaxies to giant galaxies, where dwarf galaxies have as few as a couple million stars, and giant galaxies have over 100 trillion stars. Edwin Hubble made what we call the Hubble tuning fork. It is a way to classify galaxies, and it describes all the different types that there are. And we're going to take a really in-depth look at that tonight. When you see a dwarf galaxy, you'll often find it clustered around larger galaxies, kind of how near the Milky Way we have the small and large Magellanic Clouds. And so frequently these galaxies lose their stars to their larger. Classification is important, and also that classification is doable. If you only have 2 apples, how can you classify them if they're both red? If you have one green and one red, then you're lucky. But if they're both red, you don't know if they're the same apple or if they're 2 different kinds of red apples. If you have 10 red apples, you might be able to make some different categories based on their shading and their size. So this is kind of what we're talking about when we talk about galaxy classification. Back before the 1920s, it was thought that all of the white dots in our night sky, everything that you could see with the naked eye, was within our own galaxy, was within the Milky Way. They did not know that there was anything outside of the Milky Way. They thought the entire universe was contained within it. 18th century philosopher Immanuel Kant was one of the first people to theorize that the Milky Way was maybe not the only galaxy, that maybe there were more. And he coined the term island universe to describe a galaxy, thinking that the Milky Way was its own universe. Good evening, everybody. Welcome to SLU. If you're listening, you're tuning into my Intro to Astro crash course, given Wednesday nights at this time every week. If you're joining me tonight and also joined me this morning for our super blue blood wolf moon lunar eclipse, then thanks for hanging in there. It's been a long day, but there was a nice stretch in between, and maybe there's others out there that are other mini universes. In the 1920s, Edwin Hubble was the first to confirm that the Milky Way was actually one of many, many galaxies. He did this by studying a variable star called a Cepheid variable. And a variable star just means that the light from the star is not steady, it varies. So it can vary over very different time scales, but being able to measure the varying brightness of the star, essentially it pulses. And being able to measure that allowed him to measure the distance to the star. And this variable star was contained within a nebula. So a nebula is a cloud of gas and dust in the universe. It's like a fuzzy dot looking thing. as opposed to a sharp white dot that is a star. So these fuzzy nebulae, they thought were all contained within our Milky Way, as everything else they thought was. When Edwin Hubble measured that this variable star in this nebula was actually further away, really, really far away, further than the edges of our galaxy, so maybe you took a nap. I did not, but I wish I did. But tonight, actually, we are going to venture away from the moon. So unfortunately, I already did a moon course, and so I don't have another one for you tonight. I hope you got your moon fix this morning, but we're going to venture further out into the universe, and we're going to talk about galaxies tonight. Last week, we talked all about the Milky Way and a little bit about Andromeda, and this week is a promised course on galaxy classification. So I am going to share my screen with you. So if you are listening at SLU.com, you're going to want to pop over into the space situation room where you can see my screen, because I'm going to be sharing some images with you tonight from my SLU picture file, and also some special diagrams to help show what we're going over. So galaxy classification, I think the first place to start is in the title. And the fact that we are able to classify these means that there must be enough of them that